You ever wonder what makes your computer feel so incredibly fast? It's not just about cranking up the speed, it's about the processor being crazy smart. Today we're diving deep into the secret predictive powers that are hidden inside your CPU. Okay, let's get right into it.
So here's the big question, right? We're talking about billions of operations every single second. How does the processor keep all of that straight? How does it not just trip all over itself when one instruction depends on another, or when it hits a fork in the road in your code? Well, that's the mystery we're going to solve today.
All right, so the key to all of this is a concept called pipelining. The best way to think about it is like a factory assembly line, but for your code. Instead of doing one whole job from start to finish, the processor breaks it down into these smaller bite-sized pieces: fetch, decode, execute, memory access, and then write back. Each little station does its part, and they're all working at the same time.
So, in a perfect world, here's the dream. Once that assembly line is full and humming along, a brand new, fully finished instruction rolls off the end on every single clock cycle. This is how you get that blistering speed. But, yeah, as you probably guessed, reality is a lot messier.
Yeah, because that perfect, smooth-running assembly line, it hits snags all the time. These problems, which we call hazards, can totally jam up the works. So let's look at the three main ways this beautiful system can get completely gummed up.
The first one is called a structural hazard, and this is basically a resource conflict. It's a we both need the same tool at the same time kind of problem. It happens when two different instructions in different parts of the line suddenly need the exact same piece of hardware.
Back to our analogy, it's like two workers on the line, both reaching for the same special wrench. They can't both use it, so one has to wait. And when one worker stops, the whole line stops. Everything just grinds to a halt until that wrench is free again.
Okay, that's one problem. But a way more common one is what we call a data hazard. This is all about dependency. It happens when an instruction needs a piece of data that isn't ready yet. The instruction right before it is still working on producing that result. So imagine a worker at station 2 of the assembly line who needs a part that's still being put together back at station 1. What can they do? Nothing. They just have to stand there and wait. And once again, the entire production line is stuck, all because it's waiting for one little piece of data. But those two are nothing compared to maybe the trickiest, most disruptive problem of all, the control hazard. This pops up whenever your code has to make a decision, like an if statement. In computer speak, we call that a branch. The processor is just humming along, and suddenly it has no idea which way the code is going to go next. And it's basically a fork in the road for our assembly line. The processor can't just keep feeding new instructions in because it doesn't know which path to send them down. So it literally has to slam on the brakes, and this creates these empty slots in the pipeline. We call those empty slots bubbles, and they are pure wasted potential. Okay, so if these hazards are so bad for performance, how do we fix this mess? Well, this is where engineers got really clever. First up, let's tackle that data jam, the data hazard. So a super common example is something called a load use hazard. It sounds technical, but it's pretty simple. One instruction says, hey, go load this piece of data from memory, and the very next instruction says, okay, I need to use that data right now. The problem? The data is still making its way down the assembly line. It's not ready yet, and that forces a one-cycle traffic jam, a bubble.
But the solution is absolutely brilliant. It's a hardware trick called operand forwarding. Instead of making that second instruction wait, the processor creates a special express lane. It's literally a hardware shortcut that zips the finished result right from the end of one stage back to the beginning of another, just in the nick of time. The bubble disappears, the stall's gone, problem solved.
Okay, so operand forwarding is smart, but fixing those forks in the road, the control hazards, this is where it starts to feel like magic. We're not just managing traffic anymore, we're literally trying to predict the future, and this is the whole game of branch prediction.
So the simplest idea is what we call static prediction. You can have a really basic rule, like option 1. Just assume the code will never take the fork in the road. Just keep going straight. Or, a little bit smarter, option 2. This is a bimodal predictor. It just keeps one little bit of memory to remember what happened last time, and it guesses it'll just do the same thing again.
But that just do what you did last time idea, it falls apart with something as simple as a loop. Look at this. The first time through the loop, it guesses not taken, but the loop is taken. Whoops, wrong. Then it learns, and it gets the middle part right. But on that very last trip, when the loop finally quits, it's still guessing taken, and it's wrong again. So you get 2 wrong predictions every single time you run a simple loop. That's not great.
You see the problem, right? This one-bit predictor, it's too twitchy. It changes its mind way too easily based on just one outcome. So that leads to the obvious engineering question. Can we make it smarter? Can we give it a bit of memory, maybe some reluctance to change its mind?
And the answer is, of course, yes. And the solution is so elegant, it's called a 2-bit saturating counter. Instead of 1 bit, we use 2. This gives the predictor a bit of stickiness, or what engineers call hysteresis. Now the predictor has to be wrong twice in a row before it'll flip its prediction. And boom! We've just cut our mispredictions in this loop in half. Just 1 mistake instead of 2. That is a huge win.
So, okay, we've got these cool prediction tricks inside our CPUs. But so what? What's the actual real-world impact of getting a guess right or wrong? Well, this is where we have to talk about the real price of speed.
So there's this metric called CPI, or cycles per instruction. Basically, it's how many clock ticks it takes to get one instruction done. The dream is a CPI of 1. Now, with a simple predictor that's only right 75% of the time, the CPI jumps to 1.1. That might not sound like much, but that's a 10% performance hit. It means your processor is just spinning its wheels, cleaning up bad guesses 10% of the time.
But check this out. You swap in a modern predictor that's right 95% of the time, and the CPI drops all the way down to just 1.02. That's only a 2% penalty. Think about that. We just clawed back a massive amount of performance just by being better at guessing.
And this really gets to the heart of a huge trade-off in processor design. See, over the years, engineers kept making that assembly line longer and longer, adding more and more stages. Why? Because a longer line means you can run the whole factory at a much higher speed, a higher clock speed. But there's a catch, a big one. The longer that line is, the more stuff is on it at any given time. So when you guess wrong at the very beginning, you have to throw away everything on that line. The penalty for being wrong goes through the roof.
And this quote just says it all, really. It's a high-stakes bet every single time. Correct speculation avoids stall, improve performance. Incorrect speculation must abort, flush, and recover. Guess right, you win big on performance. Guess wrong, you have to hit the emergency stop, flush the entire system, and start all over again from scratch.
So, here we are today. Our branch predictors are mind-blowingly good, like over 95% accurate most of the time. But that leaves you with this final question, right? When we've gotten so good at predicting the future that it's almost perfect, what's the next wall we're going to hit? What's the next big bottleneck that's holding our computers back?